How to Get P-Values Less Than 0.05 in Biological Research by Michael Walker. Chapter 1. Control for variables that affect the response using multiple regression, or ANOVA. Avoid t-tests. Control for variables that affect the response using multiple regression, or ANOVA instead. If you want p less than 0.05 with the minimum sample size and minimum effort, use multiple regression or analysis of variance, ANOVA, instead of t-tests. T-tests only let you test the effect of one treatment variable. This is a problem. Often more than one variable affects the response. The added variability in the response caused by those other variables makes it harder to detect the effect of the one variable you are interested in. T-tests do not let you control for the other variables that affect the response. Think of it as a signal-to-noise problem. If you are in a noisy room, it's hard to hear what someone is saying. That is the t-test version. Multiple regression and ANOVA remove the noise and let you detect the signal. The following short story, based on actual events, illustrates why you should avoid t-tests. A postdoc, whom we'll call John, was having problems with his experiment. John was studying mice in which he genetically modified a gene that might be related to weight. For his experiment, he created knockout mutant mice that lacked the gene. Then he measured the difference in weight between 24-week-old wild-type mice and 24-week-old mutant mice. Creating the knockout mice was difficult and time-consuming. After almost a year working on his postdoc, John's data looked like this. A graph comparing the groups did not look promising. John tried a t-test for the difference in weight between the mutations and wild type. Here is the R code. Here is the output for a two-sample t-test. The p-value is not significant at p equals 0.2252. The notation, grams treatment, is the formula specifying grams, is the response y variable, and treatment is the explanatory x variable. Equivalently, you can do the t-test analysis using the R function LM, which performs a linear regression. Notice the same formula, grams treatment. In the LM output, the p-value of 0.225 is in the row labeled treatment wild type, in the column labeled PR greater than T. The t-test and the linear regression both indicate that treatment is not significant at p equals 0.2252. We get the same p-value using either the t-test or the LM function. John was afraid that his academic research career might be coming to an end. Without positive results from his experiment, he couldn't publish and couldn't get a faculty position. His wife would be very unhappy if he had to start over on a new postdoc project instead of looking for a better paying job. But John believed there was a difference between the mutation and wild-type mice. When he plotted his data separately for males and females, he saw a big difference between them. John decided to try a separate t-test for mutant versus wild-type for each sex. We'll use the LM function to do the t-tests. The t-test for males gives p equals 0.137. The t-test for females gives p equals 0.153. John's t-test p-values were still not significant. He didn't want to go back and start over, using only males or only females, as that would take at least another 6 months. He wanted to use the data he already had. At this point, a colleague of his suggested that he talk to me. John showed me his results and the problem with the t-tests. I told him that, instead of t-tests, we should use a two-way analysis of variance, ANOVA. John wanted to compare the two treatment groups, mutation versus wild type, but sex, male versus female, was an additional important source of variability in the response. Two-way ANOVA is a way to control for the differences in weight due to sex, while testing for the effect of treatment group. John had used a t-test for treatment group, which doesn't remove the unexplained variability due to sex, so he got a non-significant result. John and I agreed to do a two-way ANOVA, including treatment and sex as the explanatory variables. We performed the two-way analysis of variance using the same LM function that we used for the t-test. Notice that the only change in the R code is the addition of sex in the formula. Here are the results for the two-way ANOVA, which include both sex and treatment as explanatory variables. The two-way ANOVA showed that the difference between males and females is significant at p equals 0.0002, confirming that sex was a major source of otherwise unexplained variability in the response. More important, the two-way ANOVA also showed that treatment was significant, with p equals 0.0239. John was ecstatic. His experiment was a success, he could publish, and his academic career was back on track. All thanks to using two-way analysis of variance to control for the unexplained variability that the t-test failed to control. If other variables, besides treatment, affect the response, then we want to include those variables in our analysis. Use multiple regression or multi-way ANOVA to control for the effects of factors that cause unexplained variance. The t-test is the most commonly used hypothesis test, but it does not control for variables other than treatment that affect the response. The t-test minimizes the power to detect treatment effects and maximizes the sample size required to make discoveries. Here's an example where we'll use two-way ANOVA to get a better p-value by controlling for an undesirable source of variability in an experiment. Our specific example will be controlling for variability across the columns in a 96-well plate, but the concept and the method apply more generally to other sources of variability. If you have run an experiment using a 96-well plate, you likely know that there can be substantial unexplained variation across the rows, columns, and edges. These can be caused by a plate that doesn't sit flat on the heating block, a cover that doesn't fit well and allows evaporation, problems with pipettes becoming partially blocked, and so on. Suppose you have data from an experiment where you want to know if treatment affects gene expression for control, low dose, and medium dose. Expression is measured as delta CT from polymerase chain reaction, PCR. Here are the first 10 rows in the dataset PCR.data. Here is a plot showing delta CT by treatment. We'll start with a one-way ANOVA that only considers the effect of treatment, as does the t-test, ignoring the effect of column. Here is the R code and the output analysis of variance table. The p-value in column, PR, more than F in the row labeled treatment, gives the p-value for treatment, p equals 0.0686. Using a one-way analysis of variance that ignores column, the treatment does not reach statistical significance. If we plot the delta CT values for each column, we see that there is a great deal of otherwise unexplained variability due to column. The graph shows considerable variability in the delta CT due to the column effect. Column should be included as a covariate in the analysis. Here is the two-way analysis of variance when we include column as a factor. Including the column in the model reduces the unexplained variability in the delta CT. The ANOVA controlling for column effect shows that treatment is significant at p equals 0.00129. By including the column covariate that influenced the delta CT, we are better able to determine if the treatment is effective. If we just do a one-way ANOVA for treatment, ignoring the variability due to column, the result is not significant. Instead of t-tests, use multiple regression and multi-way ANOVA to include more variables. These examples show that we get better p-values by using multiple regression and two-way ANOVA to control for variables that affect the response. In every experiment I have seen, there are other variables, similar to column, that add to the unexplained variability. The other variables might be plate, instrument, operator, rows or columns on a plate, the day, month, or year each specimen was collected, the order in which the specimens were analyzed, the source, clinic, lab, vendor that the specimens came from, the age of the animal, the sex, the litter size, and so on. If you test such variables to see if they affect the response and include them in your analysis, you are more likely to get p less than 0.05. But what if you don't know which variables are having a big effect on your response variables? How can you quickly find out which are most important? A good way to identify the important variables is to use fractional factorial designs. The chapter, Rescue Failed Experiments Using Fractional Factorial Design, describes efficient ways to design such experiments in order to look at many factors with minimum effort. Download the R code for all examples in every chapter and the free PDF companion book from mwalkerstatistics.com or order a copy from Amazon